Hello, my name is HM Ashfiqul Hamid and my presentation title today is Design, Optimization, Fabrication and Characterization of a MEMS-scale Triboelectric Energy Harvester with a high operating frequency and wide bandwidth. So in short, we demonstrated the detail of a vibrational energy harvester design that can harvest energy from any sort of ambient vibrations. A vibration is actually a very common phenomena in our regular life. For instance, if you start your car, its engine starts to vibrate. If you walk, you are exerting a pressure into your shoes and creating a vibration over there. Even while we talk, we create a vibration in our vocal cord. Now, the vibrational energy harvesters are electromechanical systems that can convert these sort of ambient vibrations into electrical energy that can be stored and used to power up small-scale sensors and regular electronics such as cell phones or smartwatches. The fundamental principle of our vibrational energy harvester is based on triboelectric effect. So this is also a very common phenomena where static charge is generated if two different materials come into frictional contact with each other. For instance, if you brush your hair with a comb, it comes into frictional contact with your hair and a static charge is generated and stored into it. Afterwards, if you bring that comb close to any paper piece, the comb will start to attract the paper pieces due to the static charge stored into it. Similarly, in winter, if you wear polyester clothing, static charge is stored in your skin due to the friction of your clothing and your skin. As a result, when you grab the door of your car, you sometimes get a static shock. The triboelectric effect has always been considered as a harmful phenomenon because it can create spark, which can lead to wildfire or damage in electronic IC. It can also create communication disturbances from aircrafts and many other sources. However, this same phenomena is now being implemented into energy harvesting, which has applications in environmental monitoring, in robotics and prosthetic systems, in space missions, and also in aircraft and automobile industry. The energy harvester design we present here has some novel features. For example, it has been scaled down to MEMS scale. So the lateral dimensions of our device is just 5000 micrometer by 3000 micrometer, which is very small. It has a high operating frequency of 1150 Hz and a wide operating bandwidth of 920 Hz. The structure of the device is comprised of two triboelectric layers. The bottom triboelectric layer is made of Teflon and it sits over a bottom electrode. On the other hand, the top triboelectric layer is made of aluminum and it's suspended through a spring. There is an air gap between these two triboelectric layers. Now, because of the presence of this spring, if this system is exposed to a vibration, this top triboelectric layer can actually move with respect to the bottom triboelectric layer. So as a result, if the vibration magnitude is large enough, you will see that this top triboelectric layer starts to collide with this bottom triboelectric layer, like it's shown over here. So when there will be collision between these two triboelectric layers, there will be friction between them, and due to the friction, there will be the generation of triboelectric charges. So in the next cycle, when these two triboelectric layers will start to separate due to the electromagnetic field, these generated triboelectric charges will start to flow through the external circuit. And because of that, we can actually see a power and output power into the load. So if this vibration cycle continues, there will be a continuous generation of power and AC power actually in the output load, and we can actually extract it. So the dynamic equations for the coupled electromechanical system is solved in MATLAB numerically to optimize the structural parameters of the device. Here are the equations for the modeling of the device. In figure 5, you can see the basic structure of the model device. This one with top view and this one is the side view of the model. Figure 6 on the other hand shows the final fabricated device. This device was fabricated in traditional clean room environment. Finally, figure 7 and figure 8 demonstrates the characterization results of the system. To conclude, we have designed, fabricated and characterized a MEMS scale triboelectric energy harvester The design can generate up to 0.6 microwatt maximum power at 9.33 G input acceleration and at 1150 Hz frequency. The linear sensitivity of the device is 43 millivolt per G. These energy harvesters can have potential applications in aircraft and automobile industry, in micro-robotics and prosthetic systems, and in wireless sensor nodes. So that's all for today. Thank you very much.